Good morning, Year 9 and 10. This is Lesson 7 of the radioactivity topic. Okay, today's driving question: how does radioactivity change with time? So, your first task is to look at these different uses of radiation and decide whether each one is true or false. Pause the video to have a go. Okay, number 1, radiotherapy kills cancer cells. That's true. Food preservation kills microorganisms. That's also true. It can sterilize surgical equipment. It's true. Clean your teeth with it. That's false. Quality control in industry. That's false. Radio tracers, so detecting leaks in pipes. True. Radio tracers in medical scans. That's true. Smoke detectors. That's true. Prenatal scans. That's false. And measuring the height of babies. That's also false. Pause to check your answers. Okay, so we're going to start by doing a practical. Okay, now if you happen to have a bag of Skittles, that would be helpful. If not, which probably most of you won't have, you can use just little bits of paper. So you can need 50 little bits of paper. So just tiny little rip like an A4 piece of paper, just rip it up into 50 pieces. And on 25 of those, you are going to write the letter S. Okay. So you're going to need some kind of cup or something to put those Skittles or paper in, okay, so that you can shake them up. So just an ordinary cup, stick the little pieces of paper in, so you've got 50 pieces in there, tiny little pieces. 25 of them you've already written the letter S on. Okay, so you're going to shake the cup, okay, and pour it out onto the desk or wherever you're sat, onto a surface. Now you need to count the number, okay, of the Skittles or the pieces of paper with the letter S facing upwards, okay? And then you're going to write that in your table over here. Okay, so you should have sketched a table, okay, where you can just jot down your answers. Okay, so the first trial in here, you're going to write down the number of Skittles or pieces of paper that have got the letter S facing upwards. Okay, so you can see that letter S, and you're going to write it in the first try column of the table next to trial number 1. Okay, so for example, if you've got 35 of those, okay, which have got the letter S facing upwards, you would write the number 35 in that box. And then you're going to put those to one side because you can say that they've decayed. Okay, we don't need those anymore. The rest of them remaining, put the rest of them back into the cup. Okay, shake the cup again. Okay, tip it out onto the desk or wherever you're sat, and again count the number with the letter S facing upwards. Okay, and this time you're going to write it in where it says trial 2, still in the first try column. So this time you might have 15. Okay, for example. So write that number in there. Then you're going to discard those, put the others back into your cup, give it a shake, and you're going to repeat. And you're going to get all the way down until you've got down to trial 4 if you can. Okay, you're going to repeat the experiment for a second time. So put all 50 back into your cup. Okay, and repeat the experiment. And this time you're going to fill out on your table where it says second try, you're going to fill out the results. And then in the final column where it says average, you're going to work out the mean of your first try and second try. Okay, so you add those two numbers together, divide by 2, and that answer goes into your average column. Okay, then you're going to have a go at sketching out a graph. Okay, so on your y-axis, you're going to have your average number of decayed Skittles. Okay, so that's in the average column on your table. And on your x-axis, you're going to have trial. Okay, so number 1 to 4. Okay, you'll do a scatter graph, so you'll do crosses. Okay, and then you'll see if you can do a line or a curve, if more appropriate, of best fit. Pause the video to have a go at the experiment. Okay, so now we're going to talk about half-life. Okay, so that experiment models what half-life is. Okay, there are 2 definitions we can have for half-life. So the time it takes the number of radioactive nuclei or atoms in a sample to decrease by 50%. So 50 is half. Or we can have the time it takes the count rate, which is the activity, from a radioisotope to decrease by 50%. Okay, so either of those, okay, are correct definitions. Now, we are going to be looking at the next couple of slides in a minute how we can actually calculate half-life from an activity graph, okay, or from a graph. But first, we're going to watch a video.
On average, different radioactive elements take different times to decay. Looking at an individual atom, it's completely impossible to tell when it's going to pop. It could happen in the next few seconds. It might take 1,000,000 years. There's absolutely no way of knowing. But when you look at a large number of atoms altogether, it's clear that on average, some radioactive materials decay much faster than others. The average time it takes half the atoms in a large sample to decay is called the half-life. It takes more than 24,000 years for half a sample of plutonium to decay. But the half-life of other elements is measured in minutes or seconds, so their radioactivity disappears much more quickly. For this reason, radioactive elements with long half-lives tend to be more dangerous than those with short half-lives.
Okay, so just remember that when we're talking about a radioactive sample, that's because the nucleus is unstable, okay? And atoms like to be stable, so they do that by emitting radiation in the form of alpha, beta, or gamma. Okay, so when we're talking about an unstable nucleus, that is a radioactive element. So by emitting that energy, that radiation, they can then become stable. Okay, and we can say they've decayed. Okay, and they're now stable again. They've got a stable nucleus. Okay, so what is the half-life of the radioisotope represented by the following graph? So you can see on the y-axis we have the decay rate, which is your number of counts per minute. So to measure the activity rate of a sample, we can use a piece of equipment called a Geiger-Müller tube. Okay, now a Geiger-Müller tube will beep every time it detects a radioactive element. Okay, so a form of radiation. Okay, and you can look at how many counts there are in a minute. The more counts there are in a minute, the more radioactive the sample. Okay, so this particular sample started off at having 80 counts per minute. Okay, so if you remember our definitions of half-life, so we're going from 80 counts, so half of 80 is 50. So we can use this graph to work out what the time taken for the count rate, the decay rate, to decrease by 50%, and that will tell us the half-life of this example. So if it started at 80, we're looking for the time taken for it to get down to 40, which is half. Okay, so the time it takes the count rate to decrease from 80 per minute to 40 per minute is 2 minutes. So we can read that off the graph. Okay, so we draw a horizontal line at 40 and then a vertical line down to the x-axis to give our time. So it tells us it takes 2 minutes to do that. Now we can double check the half-life by looking at the next one. So if we look at the time it takes for the count rate to go from 40 counts per minute down to 20, again, so that's half, 40 down to 20, that should be the same, which is 2 minutes. Okay, so we can see on the graph here, 20 down to 40 takes 4 minutes. So between 2 and 4 minutes, 4 take away 2 is 2. So the half-life of this particular sample is 2 minutes. Okay, let's have a go at a match-up activity. Okay, so you have 3 graphs on the left-hand side, and you're matching it up to what the half-life is, okay, in the middle. So half-life of 2.6 years, one of them's got a half-life of 1.2, and one of them has a half-life of 2 days. Okay, so pause the video to have a go at the task. Okay, so the answers then. The first graph, okay, matches up with a half-life of 2 days. Okay, so going down from, starts with a count rate of 80, so half of that is 40. So if you use the graph, it tells us that the half-life is 2 days. Okay, the next one, the half-life is 1.2 hours. So it starts with a count rate of 200. So when it gets down to 100, it tells us that it's 1, and it's quite difficult to get the 0.2, but it's 1.2 hours. And then the final one, okay, the half-life, the count rate starts at 100, so half of 100 is 50. So using the graph, we can see that we have a half-life of 2.6 years. Okay, let's just do one more example. Okay, so we have a graph. This time we'll use it looking at activity. Okay, so remember our definitions for half-life. We can either look at the time taken for the activity to decrease by 50% or the number of decayed atoms by 50%. So another way we can measure activity is something called becquerels, which is a different unit. So if we have a look at this graph here, pause the video to have a go at the 3 questions on the board. Okay, so the half-life of this sample is 6 days. Okay, the activity starts at 80 becquerels down to 40. So we can see that if we read that off the graph, that gives us 6 days. After this time has elapsed, 50% of the sample will have decayed. Another half-life has elapsed, so the activity of the sample will be 25%. Okay, so it starts off at 100%, so after one half-life it gets down to 50. After another half-life it gets down to 25% of its original activity, and this activity will then be 20 becquerels. Okay, let's have a look at another example. Okay, lots of practice needed with calculating half-lives. So this one here, if 1/64th of an original isotope, radioisotope is left after 1 hour, what is the half-life of the sample? Okay, so you've got to work out how many half-lives it has undergone to get down to 1/64th. Okay, pause the video to have a go. Okay, so we can see that one half-life we will be left with half the sample. After 2 half-lives we'll be left with a quarter. After 3 half-lives we'll be left with 1/8. After 4 half-lives we'll be left with 1/16th of the original radioisotope. After 5 half-lives we'll be left with 1/32th, and after 6 half-lives we'll be left with 1/64th. So it's undergone 6 half-lives. Okay, now the time taken to get down to 1/64th is 1 hour. So you've then got to work out what is the half-life of the sample. So it's undergone 6 half-lives in 60 minutes. Okay, so after 1 hour, which is 60 minutes, the radioisotope or the isotope has undergone 6 half-lives, so 1 half-life is 10 minutes. Okay, so if 6 half-lives was 60 minutes, divide that by 6, that tells us that 1 half-life is 10 minutes. Okay, let's do another example. A radioisotope has a half-life of 12 minutes. What fraction of the radioisotope will be left after 2 hours? So you have to work out how many half-lives that sample has undergone in 2 hours. If one half-life is 12 minutes, so how many 12 minutes fit into 2 hours? And then work out the fraction. Press pause to have a go. Okay, so after 2 hours, that's 120 minutes. One half-life is 12 minutes. So 120 divided by 12 means it's undergone 10 half-lives. So you can see at the bottom, each half-life, that's the different fraction we have left of the original sample. So we get all the way down to 1/1024th. That's how much will be left. Okay, so which answer is false? A, the time it takes the number of radioactive nuclei atoms in a sample to decrease by 50%. So is that a definition of half-life? Or is it B, the time it takes the count rate activity from a radioisotope to decrease by 50%? Is it C, the time it takes the number of radioactive nuclei in a sample to increase by 50%? Or is D, count rate is measured in counts per minute? So which question is false? Press pause to have a go. Okay, so the correct answer that was false was C. So the time it takes the number of radioactive nuclei in a sample to increase by 50%, it's not increase, it's decrease. Okay, now we've moved on to the final part, so the main part of our lesson. Here are your graded tasks. So there's a couple of extra pieces of information you'll need on your Show My Homework. So there is a Show My Homework assignment labelled Extra Resources for this lesson. Okay, so click on there and you will see the task for grade 4 to 5, 6 to 7 and 8 to 9. So the first task, grade 1 to 3, is to define half-life and radioactivity. So there's simple definitions. Grade 4 to 5 is an exam question. Okay, so the exam question for grade 4 to 5, which is on your Show My Homework, looks like this. Okay, so you can either print it off and write in the answer or do it on the screen. The next task is this one here, which is also on your Show My Homework. So it's a calculation, just like the ones we've been practicing. And grade 8 to 9 is also an exam question. Okay, so a little bit longer this one, 8 marks. So that's on your Show My Homework for you. So either print it off, have a go at it, or just do it on the screen. Press pause to have a go at the tasks. Okay, so now if you can get your green pen or different colour pen ready, please, to mark and correct your work and add in any extra detail you feel is missing. So, first one, your definitions. The time it takes the number of radioactive nuclei atoms or count rate in a sample to decrease by 50%. The answers to the first exam questions are in that green box. Press pause. The grade 6 to 7 task, the answer is 27 counts per minute. So the calculation's on the board. Press pause to check your answer. And grade 8 to 9 exam question, the mark scheme is on the slide for you. Press pause to mark and correct your answer. Okay, so finally then, if we could do our sentence, please. So today I achieved, state, explain, use or combine. Because I can, you need to write what's in the box, please, or summarise it. Press pause to complete. Okay, don't forget to do your Show My Homework 10 question quiz, please, on this lesson. Remember, your results will be emailed to your parents or carers, and it helps us to check that you have completed the work and also how you've got on with the work. Okay, thank you, Year 9 and 10. Have a lovely rest of your day.